All right, here we go. You've actually sort of discovered this theorem on your own. It was a homework assignment a couple days ago. I had you guys draw a diameter, and then I had you draw a chord that was perpendicular to it. So I'll give you a minute, and you can write down the name of this theorem, and then draw a diameter and try to make sure it goes to the center. Try your best on that. And then, like I said, try to draw a chord that's perpendicular to it. And there's something interesting you were supposed to be able to see with a ruler and with some measurements on here. If this is a right angle, in other words, if you draw a chord anywhere perpendicular to this, anywhere along this sort of perpendicular plane here that I'm kind of simulating here, doesn't matter where you put it, no matter what happens, if this is a 90-degree angle, this is cut in half. This is cut in half. Basically, the circle's cut in half. This 180 degrees here, 180 degrees here. And if this is 20 degrees, this would be 20 degrees. If this was 70 degrees, this would be 70 degrees. If this was 100 degrees, each piece would be 50. So it's pretty simple concept here. Like I said, you've already kind of discovered on here, at least part of this. So this diameter in this chord, of course, we're going to have the word perpendicular in here. If the diameter is perpendicular to the chord, then it's going to cut that chord in half. So I'm going to throw some numbers on here. If this was 10, you don't have to use a ruler. Let's use actual numbers on here. If this was 10, the other side would be 10. If this was 7, the other side would be 7. Kind of just makes sense, visually, logically. It's almost a postulate when you think of how logical it is. It's going to bisect not only the chord, but it's also going to bisect this curved part, which, again, just kind of logical. It's going to bisect the arc that's associated with that chord. So I'll just add a couple more little things into the drawing on here. If this was 30 degrees, it would follow this would be 30 degrees as well. Kind of just makes sense. The circle's cut in half. And then the other one down here on the bottom, I'll put 3 different arcs. I'm going to call this X. This would obviously be, this part here would be 2X. And of course the other side would be X. So it should just make sense. You had X, X, 2X. Everything's cut in half basically by this perpendicular diameter, or diameter that's perpendicular to a chord. This is going to be a big one. This is going to be a hard problem to work with, but because you're going to see this problem 2 different ways. You might just see that these are both 10, and if these are both 10 and that's a diameter, that right angle is going to be assumed. So you'll see some of the problems that right angle shows up, sometimes it does not. But if this is bisected, there's also a right angle there. If a diameter is bisecting a chord, there is a right angle. And if there's a right angle, you can use your 2 favorite things from previous chapters, trig and Pythagorean theorem. So here's the first example on the back of your page. I've got a clock up here. I really should just let you work on this. So take a second. I try to draw some of this for you. A big thing people forget to or sometimes overlook is that E is now the center point. If you see a dot on your homework problems or on a test, that's implied that E is at the center. W's on the edge, R's on the edge, T's on the edge, L's on the edge, which immediately tells you that's a diameter. If that's the center, that's a diameter. That won't be written up here in problems. It'll just sort of be implied by that point. Let me give you a couple of lengths here. This little piece, little itty-bitty segment here from the intersection to W is 2. And then from E to that intersection is 6. That's enough information. You can get all these. And maybe add this on your paper. I know I can see it's not on there. This is arc RW, so I want a degree measure for this one. This is the hardest one to do on here. This is degree measure. Some of these are easier. Some of these are a little tricky. So again, take some time. It's a great time to pause. If you really want to learn this stuff, you pause this and spend a minute. Spend 2 minutes trying to figure some of these out on your own. Some of this will be easy. Some of this is tricky. So if you look at these 3 answers, one of these is pretty simple. I think the only one that I would actually say is easy is LW. LW is a diameter, and I've essentially given you a radius. Think about what the radius of the circle is. Well, the radius is this entire length here. The radius is 8. So if this is 8, the entire diameter LW is 16. So that's an easy one. There's one other easy one on here, and that would be the other radius. ER, if you look at it, is a radius. I'm not, I'm going to draw it on here as a dashed line. Oh, sorry. This, I should have pointed this out before. You can't do this problem without that right angle box. So I should have added that on there. Apologize for that, guys. You have to either know this is bisected or that there's a perpendicular intersection. So I forgot to add that on there. Sorry about that. There's ER, and of course if you spin ER this way, of course you can see that it's congruent to the 8 because it's the same thing. It's a radius. So the first one's 8. LW is 16. Those are the two easy ones. TR is the one where you got to do a little more. You got to find this entire length of this chord. And it is a Pythagorean theorem application. You've got a right triangle here. Hopefully I'm doing that justice. One side is 6. The other side, you just figured out was 8. So if this is 6 and this is 8, you can use Pythagorean theorem to find that length. Now, I'm only going after this portion of it. You know if that's a right angle and that's a diameter, that this portion is equal to this portion. So if I'm trying to find TR, this entire thing, I can find half of it and then just double that answer, which is what I'm doing with Pythagorean theorem. So 6 squared plus b squared equals 8 squared. I think I did this math correctly. I believe that's 64, and that's 36. You subtract, I think you get 28. And of course, don't forget to take the square root. I believe it's around 5.3 or 2 rad 7 if you do it in radicals. So if this is 2 rad 7, this whole thing would be 4 rad 7. And if you do it in decimals, if this is 5.3, well, the whole thing would be 10.3. So there's your length for TR. Done. Again, it's a little tricky because it's implied you're going to draw this line on your own. This is usually not going to be given to you. The last one on here is a beautiful problem. You're going to love this. Find an arc measure, RW. I want this to be in degrees. And you have to kind of look at different parts of the drawing at different times here. This arc, if you remember, is equal to the angle that's over here at E, at the center here. And you go, well, how the heck am I going to find that angle? Well, you know how to find angle. If you know sides, you can find angles using trig. So we've done some Pythagorean theorem. Now we're going to throw some trig in here. What a wonderful situation. So think about how you're going to find angle E. And I mean angle E, I mean the angle of this right triangle. I think tangent ratio is one way to do it. I would actually recommend a cosine ratio is the best one because you wouldn't have to use this rounded value. If you do tangent, you're going to go opposite, the one we just found, over adjacent, which is 5.3 over 6. Or 5.29, I think is what it was in the calculator. Like I said, I think cosine is a little more accurate because you don't have to use any rounded values. Do your tan inverse, divide this, get a nice beautiful decimal, do a tan inverse, and the expectation in this chapter is you can do this. You get E is 41 degrees, or approximately 41 degrees, which means RW is 41 degrees. If I asked you to find arc RT, you'd probably say that's 82 degrees. Okay? Jump into the next one here in part 3.